Hello everyone. This is probably the first time you'll have seen my full face while I'm teaching, since I haven't had you for any other classes yet. But today we're going to talk about force C, okay, so Newton's third law. Okay, Newton's third law, so one thing I want you to do is make sure that when I ask a question, you at least try to think of the answer. So I really want you to try to maybe say it out loud or write it down or something, so that we're kind of engaging even though this is a video. Okay, so Newton's third law. Can you think of what Newton's third law is? Remember, the first law is inertia. Second law is F naught equals ma. So the third law is related to action-reaction. Okay, so for every action, there is an equal reaction. Equal / opposite. Okay. So, in other words, if I push on the wall pushes back. Okay? If I'm pushing down on the floor is pushing back on me. So, an action-reaction pair is fairly simple. If I push on the wall, then the reaction is the wall pushes on me. Okay? So this is the pair of two objects. So one thing that is important to note is that these forces don't cancel each other out because they're acting on different objects. Okay? So my force on the wall, that I'm applying a force on the wall, and it's going to get canceled out by the wall structure. Right? So there's some other thing behind the wall that's making sure that it doesn't fall in. Okay? And then when I push on the wall also pushes on me, and then my feet, the friction on the floor is canceling that out. So even though we have these two forces, they don't actually cancel each other out because they're acting on different objects. Okay? So give an example of this law using a hammer and nail. So the hammer exerts a force on the nail. And then that means that the nail exerts the same force back on the hammer. Okay? So when we're talking about these action-reaction pairs, it's one object exerting a force on the other object, and then the other object exerting a force on the first object. So we always have two objects involved. Okay, so let's go ahead and move on and talk about how a helicopter works. Mental note, I would suggest writing these down. You do have a key on the Schoology, but I would suggest writing it because it helps you remember. Obviously, if you need to pause the video or something and take a little bit more time understanding something, or just send me an email, that's fine. Go ahead and do that. But I would definitely write something down. Okay? So, how does a helicopter work? Well, a helicopter works a lot like a fan. So what does a fan do? A fan just pushes air in a particular direction, right? So the helicopter pushes air down. Okay? So this is why when you think of in movies, when someone's going to a helicopter, they're bending down because there's a lot of turbulence with this wind getting pushed down. Okay? So a helicopter pushes air down, but remember, Newton's third law, for every action there's an equal and opposite reaction. So if the helicopter is pushing air down, then the air is pushing the helicopter up. The air pushes the helicopter up. Okay? So that's our action-reaction pair. Now, remember, like we said before, these two forces don't cancel each other out because they're acting on different objects. So that's why the helicopter is able to take off. It just needs to push more air down. That air is going to push the helicopter up more. Okay, everyday forces. So let's talk about weight. We briefly mentioned this before, so you should be able to kind of remember this. But our weight, W, or we often just say Fg, so the force of gravity, is equal to mg. So that's mass times gravity. Okay. Remember, m is mass. That's measured in kg. Okay. G is just 9.81 meters per second squared. We don't need the negative here. Okay. Remember, negatives always have to do with direction, and we'll figure out the direction using our free body diagram. So we don't need a negative here. Okay. The other thing to note is if we went to, say, the moon or Mars or Jupiter, this G value could change. But as far as on Earth, this G value will be the same. Okay? The other force, we've also briefly talked about this one, is the normal force. So this is Fn. Okay? Now Fn is often equal to this, but not always equal to this. So for example, right now when I'm standing here on the floor, I'm pushing down. So what's my Newton's third law reaction to that? The normal force. Okay, so in this instance, it is going to be equal. But there would be other instances where it's not equal. Okay, so generally we use Fn for the normal force. So that stands for normal force. Just remember, it would be very unusual if I fell through the floor. So it's the normal force, and we measure in newtons. Okay. Remember, the normal force is always perpendicular to the surface. Okay? So if I push on the wall is going to push back with that normal force, and it's going to be perpendicular to the surface, so straight out. Now if I have an inclined plane, something like this, okay, the normal force is going to be perpendicular to that, just like that. So if I have an inclined plane, I have a box on here, there's going to be some sort of normal force that's going to be perpendicular to this. So I have a nice 90-degree angle right here. Now in this case, the normal force will not be equal to mg. Okay? So in inclined planes, it's not going to be equal. We'll see that a little bit more later, but that's one thing to remember. So how do we calculate it? Well, we need to use Fy. Okay? So we need to use the Fnet in the y direction. Remember last time we've already kind of learned how to set up Fy and Fx charts. And we add up the forces. Well, we know one force in the y direction is going to be Fn. So if I just have mg and Fn, so for example, something just basic like this, I have mg, I have Fn. Since it's not moving up or down, I know that the Fnet in the y direction is 0, right? If it's not moving up or down, that means the acceleration is 0. If the acceleration is 0, then I know the Fnet is 0. Okay? So then I know that these two things are equal to each other. So you can do 0 equals Fn minus mg, or you can skip straight to Fn equals mg. Okay? So those are your two options. Either one of these would be counted on the AP test. Okay? So you can either skip straight to here, or you can go ahead and write this intermediate step. So let's continue on. Now we need to talk about friction. So there are two main types of friction. And one is called static friction. So I want to think to yourself, what does static mean? Yeah, that's right. Static means it's not moving, right? Stationary. So static friction is for stationary objects. And then we have kinetic friction. What does kinetic mean? That's right, of course. Kinetic means motion, right? Things are moving. So this is friction for moving objects. So static friction, generally we use FF for friction. And then the formula that we have is, I'll give it to you in a second. So we have FF. You could put a little s here to symbolize static, but that's not really necessary. So friction, not moving. Okay, so this would be something where we have this, and then the box is not moving on the plane. Kinetic friction, friction while moving. Okay, so this would be friction where you're actually moving. So for example, if the box is sliding along, that would be an example of static friction. Or sorry, kinetic friction. The box is sliding along here. So one thing I want you to think about, if I have this marker in my hand and I start moving it like this, what's the force that's keeping it in my hand? Why doesn't it just slide off? Right? We know that Newton's first law, things like to stay what they're doing. So the marker prefers to just stay in the same spot. So why is it that when I'm going like this, it stays in my hand? What force is that? Yeah, the force is friction. Now, which type do we think it is? Do we think it is kinetic friction or static friction? Okay, so this is a tricky question because it is moving, right? But what we need to really think about is it moving relative to the surface? Okay, so the marker and the surface are sort of moving together. So they're not sliding on the surface, it's staying on the surface. So in this situation, it would actually be static friction because the marker is not moving relative to the surface. Now, if I'm doing this, this would be static friction because it's moving back and forth. Okay? Adhesion would be when two things stick together. This is basically just like glue. Okay? So now let's talk about the coefficient of friction. So this is the amount of friction between surfaces. Okay? In other words, if I have sandpaper and another piece of sandpaper and I try to slide them past each other, it's going to have a high coefficient of friction. But if I have ice skates and I'm sliding on ice, it's going to have a very low coefficient of friction. Okay? So this is the amount of friction between two objects. And so we symbolize this with mu. Okay? And this is a bit of a new letter for many of you. And so it kind of looks like an M, but what it really is a U. But I kind of have this extra little part at the beginning. So it's mu. Okay? Kind of sounds like a combination of an M and a U, so mu. And so you just write it by starting at the bottom like this, go up, and then you just draw a normal U. Okay? So that's our mu. And so we use mu as our variable for the coefficient of friction. Okay? And this one's actually a little strange. There is no unit. Okay? So there isn't actually a unit for mu. So let's go ahead and scroll down. Okay, so now we need to talk about how does this apply to static friction and kinetic friction. So for kinetic friction, that is mu k. For static friction, that is mu s. Okay? So it's fairly simple. Remember, we're using mu s for times when it's stationary, and then we use mu k for times when it's moving. And now let's talk about our actual formula for friction. So we have F, that's our friction, is equal to mu, I'll just put mu because it could be either one. And now I want you to tell me, when do you think the friction will be more? How can I know that I have a set value for any two surfaces. So if I have a hand and another hand, there's going to be a set amount that it is slippery, right? But what can I do other than changing the surfaces in some way to change the friction between it, right? What can I do? So one thing I can do is start pushing harder, right? If I don't want this marker to slip on the board, if I push really hard, it will actually increase the amount of friction. So the way we write that is Fn. Okay? So Ff is equal to mu times Fn. Okay. Remember, how do we find Fn? That's where we need to go back to our Fy. So we say Fy, okay. If I only have two things, then I just have mg Fn. So since it's not accelerating in the y direction, I know that mg equals Fn. Okay, so this is often true, but it's not always true. Okay, let's look at our first example. So I'll go ahead and scroll down. Both of those on the page. Okay. So, a 24 kg crate initially at rest on a horizontal floor requires a 75 Newton horizontal force to set it in motion. Find the coefficient of static friction between the crate and the floor. So, the first thing we want to do for any force problem is what? So yes, that's correct. We need to draw a free body diagram. So let's go ahead and put some forces. So I want you to go ahead and see if you can do this. So pause the video, see if you can make a good free body diagram. So I'll give you a second. Okay, welcome back. Hopefully you have a beautiful free body diagram. I'll go ahead and draw it. So one force we have is mg. Okay. Another force, remember we got to counterbalance this in some way. We have our Fn. Okay. And then we also have an applied force. Okay. So this is my 75 newtons. So I think of an applied force, Fa. Force you are doing. Okay, so this is just the applied force or the force that you are pulling. So it requires a 75 Newton horizontal force. So that's what you're doing, you're pulling on. Okay. Now, this problem is a little tricky conceptually to think about. So what I want you to do is think about, I have this trash can, okay? So I have this trash can, and I start pushing on it, okay? Right before it starts moving, the force I'm going to be pushing on it is 75, right? And then it starts moving, okay? So right before it starts moving, what's the acceleration? Right before it starts moving. Yeah, the acceleration will be 0 before it starts moving, right? After it starts moving, we'll have some sort of acceleration. But right before it starts moving, the acceleration is going to be 0. But at the same time, right, I'm slowly increasing my force, and then it starts moving. So the force is going to be 75. It might really be 74.9 repeating. But 74.9 repeating would really just be 75. Okay? So we know the entire acceleration is 0. So if I know the acceleration is 0, let's go back to Newton's second law. F net equals ma. If acceleration is 0, what's my F net? That's right, F net equals 0. Okay? That means I need all of my forces to be equal or to cancel out. Okay? So there's one more force I need here. I need an F. Okay? So what do I know about these two forces here? Remember, my F net is 0. So what do I know about these two forces? They cancel out, or I can say they're equal to each other. So I know Fn equals mg. I'll go ahead and make a chart here. This is my Fy, this is my Fx, and then I also know that Fa is equal to Ff. Okay? Because my acceleration is 0, so that means my F net is 0, so it means all these forces have to cancel out. So I got two equations here. So let's go ahead and start using these. I know Fa is 75. What's my formula for Ff? Yeah, that's right. So I have mu Fn. Okay? And then I know Fn is equal to what? Mg. So now I have 75 equals mu mg. Okay? And my mass is 24. So I have 75 equals mu 24 times, I'm just going to say 10. Okay? And then you solve for a mu. I will say, normally, mu is between 0 to 1. More than 1 would be pretty surprising. Okay, so if you get something more than 1, you might want to check what's happening. Okay? More than 1 would mean that it's actually sticking to the floor more than its weight. So that's not very likely. So I would definitely check and make sure that it's somewhere between 0 and 1. Okay? Remember, if you get stuck, you're not really sure what's happening, make sure you send me a quick email and I can try to explain something that you're stuck on. Okay, let's go to the last example problem. Okay. Remember, what's our first step for these questions? Yep, that's right. We gotta draw our free body diagram first. So, go ahead and pause the video and draw your free body diagram. Okay, I want you to practice drawing it. That's a really important skill that applies all throughout physics. So go ahead, pause the video, and draw your free body diagram. Okay, welcome back. Hopefully you have a wonderful free body diagram. And I will go ahead and draw mine. So I have a refrigerator, it's at rest on the ground. This is not drawn to scale because it should be flat. So I'll redraw that. So I have this, still does not look flat, that's okay. So one force we have is mg, another force is Fn, and then I have Ff, and I have Fa. Okay. So a 91 kg refrigerator is at rest on the floor. The coefficient of static friction between the refrigerator and the floor is 0.95, and the coefficient of static friction, of kinetic friction, is 0.9. Find the force required to set it into motion and the force required to keep the refrigerator in motion. So we're really actually doing two separate things here. We need to solve for two things. The first is just what we did before, where we need to find out how much to set it into motion. So that's where we're going to be using the mu s, so the static friction. And we also have keep it into motion. So in motion, that one is going to be using the mu k. Okay, so our mu s is 0.95, and then our mu k is 0.90. Remember, no units for mu. Okay? So let's do this one first. So let's do it in fx, fy. So fx and fy, remember, this is setting it into motion. So right before it starts moving, the acceleration is 0. So F net has to be equal to 0. So that means we know all the forces have to cancel each other out. So in the x direction, I have Fa will equal Ff. And then in the y direction, I have Fn equals mg. Okay? So we need to find Fa. So let's go ahead. Fa equals mu Fn, right? That's my formula for Ff. Then I know Fn equals mg. So I have Fa equals mu mg. So then I just need to plug in. So it would be 0.95 times 91, the mass of my refrigerator, times 10. Okay? And I can solve for that answer. Now, we need to go ahead and look at this one. And this one looks very similar. So the force required to keep it into motion. Now, if I push really hard, it's going to start accelerating, right? Get faster and faster. If I push too little, then it's just going to slow down and stop, right? So to keep it into motion, the easiest way to keep something into motion is have it at a constant velocity. If it's a constant velocity, I don't have to push extra and start accelerating it. And if I push, I don't want to push too little, so then it starts slowing down. So this one is a constant velocity. Now, if I have a constant velocity, what's the acceleration? Yeah, that's right. The acceleration equals 0, right? Remember, constant velocity, what's the acceleration? Acceleration is a change in velocity. So if a constant velocity, acceleration has to be 0. Okay? So the setup is basically identical to this one, except for the only change is now I have a different value for mu. Okay? So I have my fx, fy, I can look at my free body diagram. In the x direction I have fa equals ff. In the y direction I have fn equals mg. Right? Now I can just go ahead and start with this formula. I'm trying to find fa. Fa equals ff. My formula for ff is mu Fn. I know Fn is equal to mg, so Fa equals mu mg, and now I just need to plug in numbers. So I'll have 0.9 times 91 times 10. Okay? So that is this section here. You can go ahead and work on the problems. Remember, usually Fn is equal to mg, but that's not always the case. Okay? There are some times when that's not true, so you definitely need to be thinking of making sure you have this free body diagram so you can visually see, are there any other forces in the y direction, or is there something else that's changing? Okay? Remember, if you get stuck, if you need some help, make sure you send me an email and ask for help. Okay? That was 4C, and I will see you back for 4D.